Okay, we're continuing in op-amp applications, and in this section we'll be looking at a band pass filter and a band stop filter. We begin with the band pass, and as its name implies, it passes only a specific band of frequencies, and you can see from the graph here that that's exactly what it does. It passes a specific band, and sometimes you'll have a band of frequencies will actually be passed. This is widely used in TV, also in radio. Just as an example, with AM radio, if you were looking at AM 950 kHz, you would, it comes in, and this would be 950, and that particular band is, in the transmission, it will be 10 kHz wide, and so it would go from 945 to 955, and that would be, in this case, the band that is being passed. In television, at least in analog television, the band is actually quite wide. It's 6 megahertz wide, and so you come along and you'll have this band of frequencies, and that contains the audio and the video and the color information. Takes quite a bit more data than does radio, which is only voice. And then if we went to FM, we'd find that this is actually 200 kHz wide, because FM is going to have a better sound quality. At any rate, these are just some examples of what would of device or systems that would utilize a band pass filter. Now, let's take a look at this circuit. What we'll notice here is that we have a cap in series with the op-amp, and then we have another cap that's in the feedback loop. And so what will happen is that this cap will be very reactive at low frequencies and won't pass the signal, so no signal will get to the op-amp. Then at a very specific frequency, this will begin to pass a signal, and it will send that signal into the op-amp. We will have amplification. But notice that we have another cap in the feedback loop, and remember that the feedback loop will determine how much amplification we get, and when this begins to conduct, this will look like a short circuit, and so then we would have 0 ohms of resistance in our feedback loop, and that would cause our gain to go to 0. So what we end up here is that for a very short duration we have the passing of frequencies. And your text does not give you a formula for calculating this frequency. I happen to have one that will do it. It is 1 over 2 pi times capacitance times the square root of, and we could draw this line across here, the square root in fact it's R1 in parallel with R2 times the value of R4. And if you type that into a calculator, it will come out with this frequency, and that would be the pass band if we were using this particular circuit. Now, I built a circuit and electronics workbench. This is in fact that circuit. This was not in your package of circuits, but I just wanted to confirm the fact that this actually is the frequency. And you'll note here is our signal source. Here is the capacitor going to the input, and then here is the capacitor that's in the feedback loop. And you'll note here is the Bode plot, and I have the blue line here is capturing the point of the passing of the frequency. And you'll notice down here it's 968.9, it's about 969 hertz is that passing frequency. And what was our calculated value? Was 973. Okay, so that is really quite close to the actual value that we see in simulation. Okay, then we come to the band stop filter. Sometimes this is called a band reject filter. and we have a circuit here, and what this is going to do, and in fact sometimes they call it a notch filter, because what this typically looks like is you have a band of frequencies come along, and then suddenly there is a notch cut out, and you no longer see the signal. This, we have a formula, FR here. This is for frequency that is rejected, and this will be 1 divided by 2 pi times R1 and C1. And if we calculate this out, we'll find that this will create a notch at about, it's about 4 kHz. Let's talk a little bit about how this actually works. Low frequencies see C3 as a high reactance, and the signal is passed through R1 and R2. It looks like a low-pass filter. So going along this branch, this looks like a low-pass filter until you get to a frequency that is high enough that C3 begins to conduct, and then that signal is shunted away from the input down through C3. So the top half looks like a low-pass filter. Then C1 and C2 act like a high-pass filter. So when they get up to a certain value, C1 and C2 begin to conduct, and then it will pass a signal to the input. The circuit acts like a low-pass filter in parallel with a high-pass filter. At a specific frequency, the leading and lagging signal applied to the input of the op-amp will cancel each other out, resulting in a notch in the band. And so here we have a signal coming in here, and a signal coming in here, and the signal coming through here will, it'll come through here, but it will also go through this RC. This is actually an RC network, which will cause the signal to lag a little bit behind, and then the signal passing through here will lead that signal. They'll both reach this, and there will be a point where the two will tend to cancel each other out, and we will end up with a notch. And this is the circuit. In fact, this is the circuit that comes from your circuits in your textbook, and the calculated value was, again, it was about 4K. And when I did this in simulation, I couldn't put that blue line directly on the notch because it actually covered up the notch, so you couldn't see it, so I pulled it a little bit away from the notch. But you can see the frequency there is what, 3.981, which is very close to the value that we calculate. In fact, well, the multisim, if I put it right on there, it was actually 4.092. But at any rate, it is very close to the calculated notch. Now this one, it has a there's a little spike right here. I have seen other filters that are a little bit cleaner than that. They'll come along and they'll just be a very specific notch. And these are, as I mentioned earlier, these are used to filter out things like 60 hertz hum. Sometimes in cable systems they are used to actually notch out a given frequency that a customer does not particularly want. So these have a number of industrial uses. So in this section we looked briefly at a band stop filter. We looked a bit at the theory, and we looked at the band pass filter. And so this concludes this section.